Okay, this is our review for the projectiles test. Let's just jump in. There's a quick reminder of the guess method, and then for freely falling objects, gravity is going to accelerate these objects at 9.8 meters per second squared, and it's always down. So that's very important. And when we throw an object or launch it upward, the maximum height, the velocity is 0. These are given information pieces that we always need to know when we throw things up. So, standing on a tree 18 meters above the ground, we drop a water balloon and it hits the ground. We want to know the velocity just before it hits the ground. So, we're going to drop it. That tells me the initial velocity is 0. That also tells me we're dealing with a free fall problem, so the acceleration is gravity down. And we have our delta y. So we're going to write down all the things that we know. Our acceleration is 10 meters per second squared down. If you want to, you can use 9.8, but I like using 10 on problems like this. The delta y is 18 meters down, and what we can see here in this problem, the initial velocity is 0, is that everything is down. Since nothing is up, I don't need to throw in any negative signs. I just need to know that everything is in the downward direction. And then I want the final velocity. So, the equation we're going to use, final velocity squared is equal to initial velocity squared plus 2a delta y. We have everything, so the final velocity squared is 0 squared plus 2 times 10 times 18. So the final velocity squared comes out to be 360. We're going to square root both sides, and that final velocity comes out to 18.97 meters per second. And like we said, everything is down, so we need to go ahead and label that. How long does it take the balloon to reach the ground? Now we need the time. All the information is the same, so we're going to use the same equation. So we're going to use the first equation, v final, v initial plus acceleration times time. I could use any equation that we want to, so v final minus, so we're going to plug in 18.97 is equal to 0 plus 10 times the time. So 18.97 is equal to 10t. We'll divide both sides by 10, and that time comes out to be 1.897, well, so if we round that, 1.9 seconds is our time. All right, so we have pirates who have a citrus problem, and they attempt to fire their cannon at the ship. The cannon gets bumped, and it goes straight up into the air with an initial velocity of 32 meters per second. And we want to know what maximum height we have. So it's going straight up, which means this is all in the y direction. And we're firing it into the air, so we know that our acceleration is going to be gravity down. This is our initial velocity, and if it's telling me about the maximum height, that is what we're looking for. We're trying to find delta y. But at the maximum height, and this is super important, the final velocity is 0. So the initial velocity is 32 meters per second up. The acceleration is 10 meters per second squared down. And the final velocity is 0. Now, because this is 10 meters per second squared down and the initial velocity is up, I need to make it negative. And I want to find the delta y. So I have v initial, v final, acceleration, and delta y. So v final squared is equal to v initial squared plus 2a delta y. That's the equation we're going to use. We're going to plug everything in. V final is 0, so 0 squared is equal to 32 squared plus 2 times negative 10 times delta y. So I get 0 is equal to 1024 minus 20 delta y. We're going to subtract 1024 from both sides. So this goes away, and I get negative 1024 7. I get negative 1024 is equal to negative 20 delta y. I'm just going to rewrite that over here. Negative 1024 equals negative 20 delta y. Divide both sides by negative 20. And delta y is equal to, well, those things become positive, and delta y comes out to be 51.2 meters. And since it's positive, we know that's going to be up. All right, how long does it take the cannonball to return to the ship? This is important. If we're returning to the ship, we're going up and we're coming back down. So our delta y is going to be 0. That's another piece of information. Delta y is 0. The initial velocity is still 32 meters per second up. The acceleration is still 10 meters per second squared down. That's going to be negative. And I want the time that it takes to return to the ship. So the equation that we're going to be using has all of this in it. Delta y is equal to v initial times time plus 1/2 acceleration times time squared. So 0, my delta y, is equal to my initial velocity, 32 times time, plus 1/2 times negative 10 times time squared. So we plug all that in and kind of make it go through. 0 is equal to 32t minus 5t squared. So I'm going to bring the 32 over. So I'm going to subtract 32t from both sides. So that goes away. I get negative 32t is equal to negative 5t squared. So if I want just one t on this side, what I can do is divide by negative 5t. So 1t goes away, and the 5's go away. So I'm left with t on this side. Both these t's go away, and the negative sign goes away. So I get 32 divided by 5. That's 6.4 seconds is equal to the time. All right, number 3, we have a projectile, and I want to know the horizontal and vertical velocities. Horizontally, we'll use red for that. I know that the acceleration is 0. So horizontally, the velocity is constant. So the velocity is constant in the x direction. In the vertical direction, so vertical velocity we'll use blue for. In the vertical direction, I know my acceleration is g down. So if I start off with an initial velocity, it's going to slow down and eventually stop, and then it's going to accelerate in the negative direction. So for 3 labeled points in the diagram, tell you what, since that's not clear, we're going to go with 1, 2, and then we're going to go 3 down here. So use up, down, left, and right as our answers. So for number 1, the vertical velocity is up, the horizontal velocity is right, the vertical acceleration is down, and then the horizontal acceleration is 0. For point 2, the vertical velocity is 0 because we're at the very top. The horizontal velocity is to the right, it hasn't changed. The vertical acceleration is down because the vertical acceleration is always going to be g down. Gravity never stops pulling on our object. And the horizontal acceleration is always 0. For point 3, my vertical velocity is down. My horizontal velocity is right because that's constant and it doesn't change. The vertical acceleration is down because it's always down. And the horizontal acceleration is 0 because it's always 0. All right. So during a movie stunt, a helicopter flies forward at a speed of 50. The truck is directly underneath it, also moving at 50. And the stuntman drops from the helicopter. He's going to land right inside of the truck because both the stuntman who's falling, so we'll write down both the falling stuntman sorry, both the falling stuntman and the truck have the same horizontal velocity the entire time. This would be just like you're driving in your car and you're holding a piece of trash in your hand and you drop it down into the other hand. Everything's moving forward with the speed of your car at the same time, so it's just going to fall straight down into your hand. As the truck moves forward, the stuntman moves forward at the same rate. Number 6, we're going to, from a 45-meter tall cliff, we're going to fire a cannon horizontally with an initial velocity of 120 meters per second. So if we're firing this thing horizontally, one of the things that we automatically know is that the acceleration in the y direction is g down, the acceleration in the x is 0, the initial velocity in the y is 0, and this initial velocity is in the x direction. And it's a 120-meter tall cliff. That's our delta y. So we have x information and y information. So if we want to figure out how far away the cannonball lands, we need to do x stuff and we need to do y stuff. So in the x direction, I know that the acceleration is 0. I know that my velocity in the x direction is 120 meters per second because it says it's fired horizontally, and so whatever initial velocity I have is all pointed in the x direction. And that's all I know in the x direction. In the y direction, I know the acceleration is 10 meters per second squared down. I know the initial velocity in the y direction is 0, and I know that my delta y is 45 meters down. So for these problems, the first step is always, unless it's given, find the time. Well, I can find the time in the y direction because I have enough information. I've got delta y is equal to v initial times time plus 1/2 acceleration times time squared. So 45 is equal to 0 times time plus 1/2 times 10 times time squared. That goes away. And so I have 45 is equal to 5t squared. Divide both sides by 5. Those 5's go away. And I get t squared is equal to 9. So the time, when we square root both sides, comes out to be 3 seconds. So over here in the x direction, I know that my time is 3 seconds. So if I want my delta x, it's velocity times time. So delta x is 120 meters per second times 3 seconds. Seconds goes away. And my delta x comes out to be 360 meters. What could be changed about this situation to increase the time it takes for the cannonball to reach the ground? Time is a y-only question. The only thing that you can do to increase the time is increase the height. Nothing else will increase the time. Changing the velocity in the x direction is an x direction change, so it won't increase the height. Changing the height in the y direction will increase your time. That's how we found the time. That's what's going to do it. What could be changed to increase the horizontal distance? Well, we said delta x was that velocity in the x direction times time. So we could increase the initial velocity in the x direction, or we could increase time by increasing the height. That would increase the horizontal distance the cannonball travels. Number 7, baseball player throws a pitch horizontally. Again, that's going to tell me the initial velocity in the y direction is 0. The speed of 50 meters per second, that's the initial velocity in the x direction. And when it reaches home plate, 15 meters away, that's our delta x. How far has the ball fallen vertically? That's our delta y. I need you, when you do these problems, to mark the text with circles or boxes so that you know what your given information is. Because it gets more complicated the further we go with this. We're going to look at the x direction. We know that the acceleration in the x direction is 0 because gravity pulls down. We know that our delta x is 15 meters away, and we know that the velocity in the x direction is 50 meters per second. So in the y direction, we know that the acceleration is 10 meters per second squared down, but we don't know our delta y. We do know our initial velocity in the y direction is 0, again, because it's thrown horizontally. So we don't have enough information in the y. We have a whole lot of information in the x. So we need to find the delta y. To get that, what we're going to do is find time in the x. So I know that, I'll move over this way a little bit, delta x is equal to velocity times time. So 15 is equal to 50 times time. We'll divide both sides by 50. And that time comes out 0.3 seconds. So we're going to take that time and we're going to use it over here to find our delta y. So the equation that we're going to use to find our delta y is equal to v initial times time plus 1/2 acceleration times time squared. So delta y is equal to 0 times 0.3 plus 1/2 times 10 times 0.3 squared. So delta y is equal to So that comes out to be 0.45 meters. The ball drops 0.45 meters. All right, last question. During a high-speed police chase, a car goes over the cliff 20 meters high. The car lands 60 meters away. So it's going to launch itself horizontally. That means the initial velocity in the y direction is 0. It's 20 meters high, that's our delta y. We land 60 meters away, that's our delta x. So if we want to know how fast the car was going before it left the cliff, that's the initial velocity in the x direction, because as we leave the cliff, we're going to fly off horizontally. So we have x stuff and we have y stuff. We know that our acceleration in the x direction is 0. From the problem, we see that our delta x is 60 meters away, and if we want the velocity, it's going to be delta x over the time. That's what we can use when the acceleration is 0, but we need the time. So in the y direction, the acceleration is 10 meters per second squared down. The delta y is 20 meters, that's also down, and the initial velocity in the y direction is 0 meters per second. And I can use all of that information to find the time. The equation that goes with that is delta y is equal to v initial times time plus 1/2 at squared. So we get 20 is equal to 0 times time plus 1/2 times 10 times time squared. That goes away because it's 0. So we get 20 is equal to 5t squared. We'll divide both sides by 5. I get t squared is equal to 4. Square root both sides, and t comes out to be 2 seconds. So we'll take that, plug it in over here, and we see that the velocity is equal to 60 meters divided by 2 seconds, or it's 30 meters per second. That's how fast the car was going. So if the velocity of the car were to be doubled before it goes over the cliff, how the horizontal distance the car travels before reaching the ground changes? So this is what's going to happen. The velocity of the car is doubled. So the horizontal velocity changes. So if we look at delta x is velocity times time, well, if we look at our little expression, velocity is equal to delta x over time, we're going to multiply the velocity by 2. We're going to double that. But time doesn't change because we can only change the time by changing the height. If we don't change the height, we don't change the time. So by doubling the horizontal velocity, my delta x is velocity times time. So my delta x is 60 meters per second times 2 seconds. We end up going 120 meters. We double the distance.